This is the recording for Terminology and Notation of Sequences and Series, an introduction to Unit 1, Chapter 1 of Mathematics 2200. So we'll introduce some terminology and notation associated with sequences and series. Not everything for the chapter, but some basics to get you started. In Australia, in the mid-1800s or so, some rabbits were imported, about 24 pairs of rabbits. The result was a population explosion because there were ideal conditions for rabbits to reproduce. Here's how it worked. A pair of rabbits have to be at least 2 months old in order to reproduce. So let's say you started with a pair of rabbits, and at the end of 1 month they're not old enough to reproduce, but at the end of month 2 they are. And every time they reproduce, they can be expected to produce another pair of rabbits. The other catch is, after 1 more month, that same pair can produce another pair of rabbits. So let's see what happens here at the end of month 2. At the end of month 2, you've got a new pair of rabbits have been produced, and you've got your original pair. Now at the end of month 3, that pair, the original pair, can produce yet another pair. This pair that was produced back here, they're not old enough yet. So come on down here, here's your original pair. They can produce yet another pair, whereas this pair was not old enough to produce yet. Meanwhile, over here, these guys, they got old enough to produce, so now you got them plus yet another pair. The pattern is 1 pair, 1 pair, 2 pairs, 3 pairs, 5 pairs. If you add up each pair of terms, 1 plus 1, that will give you 2. That will give you the number of rabbits for the next month. 1 plus 2 equals 3. That's the number of rabbits for the next month. And 3 plus 5, 2 plus 3 rather, equals 5. And 3 plus 5 will give you 8 pairs of rabbits after months, at the end of month 6. So imagine if 24 pairs of rabbits had been imported, 8 times 24 works out to 192 rabbits in just 8, or pairs of rabbits rather, in just 8 months. That's an example of a sequence in real life. You can find that sequence is called the Fibonacci sequence in many other patterns like pine cones and snail shells and male bee family trees. Okay, as we've seen, a sequence is really just a pattern. You've got a bunch of terms of some sort that are connected by a pattern. So for example, we could have a bunch of geometric figures here. Each figure is formed by adding 3 blocks or squares to the previous figure. Here, the terms are increasing by 5 all the time. It doesn't have to be an increase or a decrease as such. As we saw with the Fibonacci with the rabbits, the pattern was add a pair of terms to get the next term. So a sequence is an ordered list of objects that follow some pattern or rule. It can be a finite sequence where there's only a certain number of terms, or it can be an infinite sequence where the terms go on and follow the pattern forever. The only difference between a sequence and a series is that a series adds the terms of the sequence. So once again, we have either a finite series or an infinite series. And we know we have an infinite series or sequence if these ellipsis points have been used. Now I've constructed here a table of values to represent the terms of a sequence. Let's say we had a sequence 2, 6, 18, 54, 162, etc. This term occupies the first position in the sequence. This term occupies the second term or second position, etc. down the road. If we don't know the exact position of a term in the sequence, we'll say it's at the nth position. We use the subscript system to keep track of the terms that we have in a sequence. So for example, T sub 1, that's the way we read it, T sub 1 represents the first term, T sub 2 is the second term, T sub 3 is the third term, etc. T sub n is the nth term, also known as the general term. So for example, if I had this sequence, -1, -3, etc., Negative 1 would be the first term, t sub 1, t sub 2 is this one, t sub 3 is this one. Again, remember, the subscripts refer to the positions of the terms in the sequence. The subscripts are not the terms themselves. Now, I want to talk a little bit about the nth term versus the previous term notation. Term 4 would be the term previous to term 5. We can think of the subscript, instead of being just a 4, we can call it 5 minus 1. Term 3 would be the term previous to that term at the fifth position minus 2. So if I apply the same thinking up here, the term previous to t sub n would be the term at the n minus 1th position. The term previous to that would be a term at the n minus 2 position. So the position of the term previous to t sub n is the n minus 1th position. The name of that term, though, would be t sub n minus 1. Meanwhile, the term after t sub n, well, that's one position after, so it's t sub n plus 1. Then we have t sub n plus 2, etc. Last, a reminder that the natural numbers consist of the numbers 1, 2, 3, 4, 5, whereas the whole numbers start at 0, and the integers have negatives. Pay close attention to these subscripts we've been using, 1, 2, 3, 4, 5. They're always natural numbers because they refer to the positions of the terms. It does not make sense to have a term at the negative 2 position. And likewise, it's not possible to have a term at the 0th position either. So therefore, the domain of a sequence is generally considered to be n such that n belongs to the natural numbers. In summary, a sequence is an ordered list of elements connected by a pattern. T sub n is the nth term, also known as the general term. T sub n minus 1 is the term previous to that. T sub n minus 2 is the term previous to T sub n minus 1, etc. A series is the sum of the terms of a sequence, and the domain of a sequence is generally considered to be n such that n belongs to the natural numbers.